All right, for this next example 4, find the intervals on which this function f of x equals x squared minus 2x minus 3 is monotonic. So remember, monotonic essentially means always increasing, always decreasing, one of the two. So if we want to know where it's monotonic, essentially this is a way of saying find the intervals on which the function is increasing or decreasing. So we want to know where's the function increasing, where's the function decreasing. So the easiest way to figure out where a function is increasing or decreasing is to sort of take the number line, the real number line, the domain of the function, and split it up into these smaller little pieces. Now, we've just learned that increasing is if, one way we can check if a function is increasing is to check to see the sign of the first derivative. So if the first derivative is positive, that means the function is increasing, and if the first derivative is negative, then the function is decreasing. So what we could do is find where the first derivative is 0. Then, if we know where the first derivative is 0, that means at every other location, it has to be either positive or negative. So it's these values, these 0 values for the derivative, that kind of split the real number line up. If you think of the real number line as a long string, where the critical points are, that's going to cut the real number line. It's going to divide it into these regions, like region 1, region 2, region 3. And if we know that the function's derivative is 0 at these locations, that means the function flattens out. So this is either a peak or it's a valley. Same thing here. This is either a peak or a valley. So then if we have uphill, downhill, we can go ahead and find mins and maxes and all that stuff. But for right now, let's work on finding where the critical points are. That will allow us to split up the real number line into these distinct regions, and then we just need to take a sample point. So, to find critical points, let's go ahead and do a derivative. So the derivative here is going to be 2x minus 2. Since this function we began with is a polynomial, it's continuous and differentiable everywhere. So this first derivative, it exists. We don't have to check DNE. So I'll just say comma exists. And then that means that we're going to have to see where the first derivative equals 0. That's the only possibility for a critical point. So if we set the derivative equal to 0 and solve, we'll get x equals 1. So the function f has a single critical point at x equals 1. So now if we take the real number line, which is the domain for this function, then we can split it up at our critical points. What do we know about the critical point? Well, we know that at x equals 1, the first derivative is 0. So I'm going to put a 0 above that to let us know that the first derivative, f prime, at this location is equal to 0. So effectively, this splits the number line into two regions. We have the region from negative infinity to 1, and the region from 1 to infinity. Now we know the derivative is 0 here. And since the function is continuous, there's no way, so for instance, if we go ahead and we take a sample point, let's go ahead and say x equals 0 for a sample point. Well, if we plug this into the first derivative, right, f prime of 0 is negative 2. So that's negative. So we know that it's going to be first derivative, f prime, is going to be negative. It's going to be a decreasing quantity, f is. So if the first derivative is negative right here at this sample point, we know that if I pick some other x value, let's say x equals 1/2, bigger than 0 but less than 1, we know that the first derivative is also going to be negative here. Why? Because if our first derivative, right, it's a polynomial, so it's also continuous. So if that varies continuously, there's no way we can go from a negative to a positive here unless in the middle there was a 0. We know there's not a 0 in the middle because we looked for all of our zeros, and the only 0 we found was right here. So if our first derivative does change signs at all, it would have to happen across this 0. Doesn't have to. We could have a function that is doing something like this. Going downhill, flattens out for a second, and then it continues downhill. Right here, at this flat tangent line, we would have the first derivative is 0, but it would be negative after those locations. So it is possible to have minus, 0, minus, but as you do these problems, you will see that they typically oscillate, not always. But right here, let's just do another sample point. Let's do x equals 2 for our sample point. F prime of 2 is in fact positive. So what we see is that f is increasing on, not 0, excuse me, 1 to infinity, right? This half of the real number line from 1 to infinity, and f is decreasing on negative infinity to 1. So we could say f is monotone on negative infinity to 1, and it's monotone on 1 to infinity. It's not monotone everywhere because at x equals 1, it switches from increasing to decreasing. But if you look at any two values in this interval, monotone, and anywhere in this interval, monotone.